So the last thing we had last time. Then the elasticity of R was equal to 1. The class group is trivial. No surprise there, because of course if the elasticity is if your class group is 1, that means that the class group is trivial. So this is D. And we proved this last time. It's a cute little thing. Let me give you a corollary, which is a theorem you already know, but I always like to kind of think. Here's a slick way to do the Carlitz theorem now. If well, yeah, R is reinvented. Then R is an HFD. If and only this is a direct corollary note. So you can use this theorem here, the Valenza Narkiewicz theorem, to do the heavy lifting for you. If so let me kind of make that remark at the beginning of the book, or at the beginning of the proof. The class number 1 in ours, UFD, for instance, an HFD. And we actually have the if and only if in the case of a class. Well, we have class group is 1 that is UFD, therefore an HFD. Note that if R is an HFD, let's go this way. If R is an HFD, then the elasticity is 1, right? And so notice that this first case is covered in my guard sentence there. So suppose you have a HFD, and let's suppose the class group is greater than 1. I claim that this needs to be this one. So we'll break this down into 2 cases. Well, let's see, we have that R is an HFD, so, the elasticity is 1. I claim that, the class number has to be, greater than 2. So, case 1, let's suppose the class group is not cyclic. Then, let, And CLR has a subgroup isomorphic to where H corrects, okay, so it decomposes somehow, right? And this. These two elements from here is a collection of two elements with no zero subset. So CLR is bigger than 2. Whoops. So Davenport constant. And this would give a contradiction. But Davenport constant is bigger than 2. You can't have elasticity 1. Right? So this reduces to case 2. Is cyclic. And in this case, we have Davenport constant of CLR is precisely equal to the order of CLR. We showed this last time for a cyclic group. Therefore, so what we've shown is if the order of a class group is greater than 1, the only choice is it must be 2. All right, because anything exceeding 2 will defy elasticity 1. On the other hand, the other direction is easy. The order of class group is less than or equal to, then it's either or the order of class group is less than or equal to, and row of R is equal to 1. Because the only group of order 2 is Z2, which is cyclic, and Davenport constant. So that's how the Carlitz theorem, we've actually kind of done the heavy lifting with the Valenza Narkiewicz theorem sort of generalizes this in a certain sense. Okay, any questions on that? Yes.
So for the CLR is not cyclic, why do we say subgroup isomorphic to H plus K? Can we just go full out with like
yeah, you could, if you like, I mean, we certainly know that the class group is finite, right? So you could put it in the invariant factor decomposition, right? But I could certainly take the invariant factor decomposition, H1, some H2, some right, HK, right. I can just take the first 2 to be my relevant subgroup. Right. Okay, other questions? Let me point out something that is kind of a fun observation to make. Oh, actually, the last little bit, excuse me, in this class is I'm going to talk. We'll just see how far we get. Talking a little bit about Noetherian rings. So I'm going to give you some some business on this. We'll learn like Nakayama lemma and so forth. Noetherian rings are arguably the most important class of rings studied in community algebra. A lot of what I do does not involve Noetherianness, but you know, some of it does. What's cool about Noetherian rings? Well, Noetherian rings are, one might argue, easier to study from one point of view, in the sense that their ideals are all finitely generated. Right, so you can do lots of computational things with it. When you've got a finite number of generators for every ideal, you can do some stuff that's more computational than you can in the general case, and you get sharper results for Noetherian rings. If you're assuming that all your ideals are finitely generated, you can look at these kind of specialized stuff with it. So here are some. We're going to highlight some of this. A lot of these theorems are kind of review. If R is Noetherian, here all my rings have one, then so is Rx. We actually proved something stronger earlier, that if R is a commutative ring with identity, then R is Noetherian, and so is R of X. And in fact, if R of X is Noetherian, this forces R to have a one. So if you remember, we pointed out earlier that if you don't have a one, then Rx is never Noetherian. Theorem 602. Here is sort of the tandem result for power series. It won't look at it as far like it at first, but I'm going to capture a corollary. Suppose you have a power series ring R power X, and suppose you have a prime ideal P. So P0 is the image of this prime ideal under the homomorphism that annihilates the variable. Then P is finitely generated. If and only if P0 is finitely generated. And actually, I'm going to get a little bit more specific than that in the following sense. And in fact, if P0, here, you can read it. In elements. So if you find that P0 is generated by n elements, then P can be generated by n plus 1 elements. X and n elements if X is not in P. Now, if you remember, let me take you back to it. I'm gonna be, I should be ashamed for doing this, but not too much. I did this a little bit better, maybe not a great deal when we first did it, but let me kind of sketch why this is true, say for one generator, just to give you the feel for why this is true. Suppose that P0 is generated by A, right? Downstairs, right? Now the claim here is that the original P can be generated by either one or two elements, depending on whether X is why is this true? Well, what do I know about this? Well, let's write this down as actually, let me call this I. It's A0, it's A1X, A2X squared. Like this. Notice that A0 is in pi. Well, yes, this is certainly true. I agree with that, because when you annihilate the variable, all you're left with this, that's b in pi. So, if X is in P, then P is generated by pi X, right? Everybody agree with that? Because really, all you got to be able to, if X is in the prime ideal, all you really got to do is be able to generate that constant term. And once you do that, you've got complete freedom with this X. You can tack on whatever you want, right? So there's your two generated case. Now my claim is if X is not in pi, or not P, then choose f of X certainly there has to be some f of X whose leading term is this generator, right? Now, let g of X be in P in general, and I claim that it's got to be a multiple of this. Well, note that g of 0 is R0 pi, right? Because it lives in P, right? So g of X R0 pi plus C1X plus C2X squared, etc. And if you look at g of X minus R0 f of X, well, of course, this is designed to make that first term cancel, right? And so what do I get? I get, this is D1X plus D2X squared plus D3X cubed after combining this, right? After all that.
Not right thing.
But X is not in P, therefore, and D, which implies that D1 is in high. And now you get your second divisor. You keep this process going. And if you continue this, you get x times g of x, which is exactly what we wanted, right? Notice prime here was very important, right? Because you had to be able to argue at this juncture here that because this is not in here, this other one has to be in here, forcing this one to be divisible by pi. So we did this in a little bit more detail earlier, but that's the gist of it. Let me give you a couple of important corollaries to this. Number one, here R is the Noetherian. Again, all my rings have one. Then so if you have R, if it's Noetherian, then it's power series ring test. The proof is very different from the proof of the Hilbert Basis Theorem, where you actually kind of reduce things by degrees and you say, if there's finite number of things left over. Let gamma in our power X be a prime ideal. Uh, if you look at its image, gamma 0 and R, this is generated by finitely many elements, we'll say n of them. And I know this because R is Noetherian, right? So that ideal has to be finitely generated. Therefore, gamma is generated by n plus 1 elements. So by the previous result, we have that gamma, the original, can be generated by n plus 1 or maybe n, but certainly n plus 1 elements, right? So as every prime ideal is finitely generated, R power X is Noetherian. Any questions so far? Corollary 604. Here, R is a principal ideal domain. Then R power X. This one's rather interesting. Let's go through this actually.
We use the every non-zero prime as a prime element.
That's exactly what we want to do. Proof. Oops, gamma. The a non-zero. Prime ideal. But gamma, not very far, might be.
Images principle.
Yeah. Actually, there's something wrong with someone I want to work with this. This statement, by the way, is true. Oh, well, maybe not. Let's see. Yeah, no, I think we're good. No, we're good. We're good. Okay, so what gamma zero, well. Yeah. What happens if the image is zero? There you go. Of course, X is a prime element of power three ring, because we went out by to get that. Right. So if A is zero, then there you have it. If then what happens?
What's the difference, right?
F of X such that F of zero equals A generator. It must be a generator of gamma, right? Because this is the case when X is not in, here, that, then this is, well, actually, I should have taken this part here. Let me add a statement to this. If in general, and not just in this case when A happens to be zero, but in general, if X is in gamma, then it contains a prime element. So we can assume that X is not in gamma, and hence A is not zero, because we're assuming that gamma is a non-zero prime ideal. So there must be some non-zero element in it, and since X is not in here, let's have A is non-zero. Any questions so far? So gamma is generated by F of X such that F of zero equals A. In fact, there may be many choices for this, but they'll all be associates. It's fine. Right. So, I shouldn't have even done A equals zero. There's nothing wrong with it. It's just this unnecessarily confusing. If you have X's in gamma, the gamma contains a prime element, we can be done with it. So we can assume that X is not in gamma, right? In this case, you must have some element that has a non-zero constant term. And gamma must be generated by this, because this is the case where X is not in P, so it's generated by one element, just like down in R.
And
So f of x in gamma is desired non-zero prime element. Seems doable, so how do you adjust this a little bit so I can make this better? In fact, this goes even further. So in fact, you can actually do this for any number of variables, as long as the coefficient brings PID. So looking at this proof, how do we adjust this to get the full result? Notice, here's another theorem that I believe that we talked about earlier. If R is a UFD, then so is Rx. UFD transfers up to polynomials, therefore so is R x1, xn. So in fact, R in any index set of indeterminates, UFD, these are all UFDs. R is UFD, polynomial ring, uncountable limited variables, you're good to go. It's limited in power series. Why is it limited? Why do I keep the variables finite instead of possibly an infinite set of variables?
Not really clear what we mean.
Yeah, that's right. That's a whole new can of worms you have to open, because if you have infinitely many power series indeterminates, there's at least 3 distinct definitions in the literature of what that means. You can argue over this, and I'm not gonna let that genie out of the bottle. So how do we mimic this and get this better? Notice that this theorem says if you're a PID, then the power series is UFD. Here, I just say UFD. How do I mimic the proof here to get if R is a UFD, then its power series ring is? And you're right to say nothing, because you don't, because it's not true. All right. So here's a little hazard. Here's the simplest example I've seen. Let me check that. I think it's like. I want to make sure that got the numbers right here. Oh, then this ring is a 2-dimensional UFD. Here, let me make clear. K is in. So you've got a polynomial ring in 3 variables, and you mod out by this relation here. So x squared is basically equal to negative y cubed minus z7. By the way, we will not be proving this juncture. But if you mod out by this drops the dimension to 2 from 3 dimensions down to 2. This is a 2-dimensional UFD. If you look at R power t is not a UFD. Historically, the first example of such an occurrence was written, I think it was 1968 by Samuel, came up with an example. his example is a little bit different. This one's more streamlined. But it is possible to have a UFD. And here's the thing. Look at this right here. Remember, a principal ideal domain is synonymous with a one-dimensional UFD, right? So in other words, R as a UFD implies R power X as a UFD is okay in the first dimension. And it fails at the earliest possible opportunity, right? 2 dimensions is a little bit too big. And so in other words, this counterexample is really raining on your parade, right? In the sense that this is, when you have a PID that is a one-dimensional UFD, this always works. And it sometimes doesn't work for 2 dimensions. There's been a lot of theory that goes on. After Samuel's example 68, there were this whole industry of papers that came out with variants on this construction. And there have been a lot of work. I mean, does every 2-dimensional UFD fail? Absolutely not. In fact, if I walk up to you on the street and give you a 2-dimensional UFD, power series is probably a UFD. But there are large classes of counterexamples that one can find. So that is just another lesson in power series can be bad. Okay, any questions on that? Okay, let me give you a theorem that we are going to use. I'm going to more or less use this as a lemma for the Krull Intersection Theorem. This one's hard to keep track of. I always have to think about this one quite a bit. Okay, so let R be the theorem. You've got your favorite Noetherian ring. I an ideal, A a finitely generated R module. Ideal, A finitely generated R module. And B a submodule of A. So you've got the specialized module I, because it's in fact an ideal. A is just some finitely generated R module. B inside of A is some submodule of A. And let C be the submodule of A, which contains IB, a submodule, yes. Let C be a submodule of A, which contains IB. Of course, we found that of course I is an ideal is part of R, B is an R module. So if you look at IB, that's going to be a submodule of B that's contained in B. And C has the property that is maximal with respect to all children, because such a thing exists along the way. So C is maximal with respect to the property that C intersect B equals IB. By the way, the existence of such a submodule, well, I'll talk that through when I get done writing. Then I and A is in C. And for some positive integer n, I, the nth power times A is actually contained can see. So let me kind of try to make a little bit, I know there's a lot of stuff in this theorem. It's hard to kind of wrap your skull around a little bit. So R is an Noetherian ring with an ideal I. A is some random finitely generated submodule. B is a submodule of this. And so of course, IB is contained in B, right? So C is some submodule that I find, submodule of A that contains IB and is maximal with respect to this property here. Let me point out that C contains IB, and notice IB satisfies this property, right? Because IB is contained in B. So if I put an IB there, I get equality, right? So I'm not completely making this up. Such modules exist. C happens to be maximal with respect to this property. Then the conclusion is a large enough power of I blasts A inside C. Okay, so let's look at the proof of this proof. So the first thing I'm going to do is I'm going to reduce the problem a little bit. Since I is finitely generated, it suffices to show that for all x and I, there is m and n such that x to the m a is contained in C. Right? Because all you have to do, so if this is true, if every x has its own one, then all you have to do is pick the n's for the generators and take an appropriately larger power of this, and this will certainly happen, right? Because IN is generated by products, products of these things. Everybody okay with me so far? Okay, we define Dn to be the submodule of A. D is going to be a particular submodule of A that we define thusly. It's all A and A. Such that AN, oh, no. So for a fixed value of X, we define Dn to be the set of everything in A such that the nth power, hence the n here, knocks A into C. These submodules form an ascending plane. So it's easy to see that D1, D2, D3, etc. And of course, A is finitely generated in R is Noetherian, so these must stabilize. We'll say that it stabilizes at I should write this way, and I now claim, I'll make the following claim here. I claim that, XMA I claim that, XMA plus C intersect B is equal to IB. Notice that, this containment is clear, isn't it, right? Because IB is certainly in B, and IB, is C by hypothesis, and of course, C contains the rest of this chunk. So we've certainly got this. All right. For the other containment, we're going to suppose that T is in the left side of this. I suppose that T is in here. So T is in B and T is in the other piece, so that I can write T equals and then of course is also in B. I use my notation suggestively. Little a is in A, little c is in C. Then XT is in XB. Which is contained in B, or better than that, it's contained in IB, which is C. And so, x to the m plus 1 pages. So, remember, this thing stabilizes at m, right? This ascending chain here stabilizes at m. So what this means is x to the m, A is in C. And so T is in C. And what does that get us? Well, since T is in C, it's also in C intersect B, which is IB. This gives quality of sets above. It's I guess the harder containment, if you will. By the maximality of C, since C is maximal, we must have X, M, A. And by the way, let me point out, I don't think I mentioned in the proof that, of course, its maximality must exist by the ascending chain condition. This is a good place for today. Any questions? This establishes the limit. We're going to use it next time for the Krull intersection, Krull's intersection theorem. Let me also remind you, I haven't looked yet, but are there any there any questions on here?